Now it claims it's recording.
Yes. Thank you, everyone, for coming for the fourth meeting. And this is a continuation of maybe this is the fifth meeting, I think, and this is a continuation of the third meeting. Last meeting was just a review of all the stuff we did and a big picture idea. And we are using James Oxley's Matroid Theory book. And let's begin with the review. Excuse me. So normally we start with independent sets, but today we're just going to sort of consider that, done. Circuit axioms 2 and the basis axioms 2. Now, we'll use the rank function. So let me just quickly mention that. The rank function is just a function from the power set of E to the natural numbers and or 0, such that it's the rank of X is the size of the largest independent set in X. And the rank axioms, the rank function satisfies these three axioms that we're calling the rank axioms. And in particular, the third one, any function that satisfies the third one is called submodular. So the closure function is a function from the power set of E to the power set of E, defined as the set of all E such that rank of X union E is equal to rank of X. It's somewhat topological in nature. So you have the set X and you have, all the elements outside X that will not increase the rank of X, right? And you just sort of throw all that in. And the closure function satisfies these axioms. And I think we're going to use number 3 in some of the stuff we're doing today. Okay, so a set is closed, or otherwise known as a flat, and they're just really the same thing if the closure of F is just F itself. And the flat axioms satisfy these properties, and it's just 3 of them, and from them you get this other property, and that's also something that we will use, that if you add one more element to the flat, it's closed, right? So it's going to increase the rank by 1. And finally, the hyperplane axioms, that's just there. So if there's a hyperplane around, I'll mention it. And then we had this example. This was our geometric representation. These are not graphs anymore. They're incidence geometries. They're points and lines that satisfy the usual properties that you would expect points and lines to satisfy. And the lines are the flats. So you have the empty set, then the single element flats. This is what we call a simple matroid. There are no parallel elements, there are no loops. And these are the lines. Now, the 3-point lines are the only lines that are drawn. So sort of the non-trivial lines. The other lines, like there is a line through 4, 5, there's a line through 4, 3, and the figure would get very cluttered if we drew all those lines. So just by convention, we only draw the non-trivial lines. And these are all the lines, the trivial and the non-trivial one. And then, of course, the entire set E. Now, these
excuse me.
Sure.
In this environment, do you assume that 2 points determine at least one line, or no?
Yes. So,
okay. So there are lines between 5 and 6 also, and things like that. Yes.
So every pair of points determines a unique line. And what I've drawn is a 2, 5. Yeah, so it's written in green. A line has at least 2 distinct points, and 2 lines intersect in at most 1 point. Those are the rules. And here, this line 253 is a 3-point line. It's a non-trivial line. And that's why we draw it. We don't draw the trivial lines. The figure would just be too much.
Okay. But
Yeah.
still, your green rules don't include the rule that 2 points determine at least one line, right? You say that 2 lines intersect, but
Well, that's a good question. I think it follows from this, but I'll have to look up and figure out exactly how, because the points and lines are interchangeable in a rank 3 figure, right? So if you look at it from the top,
in the standard theory of so-called incidence configurations, you can just think of lines as being specified subsets without a geometric assumption, as is done in the theory of affine or projective planes, that pairs of points determine at least one line, that kind of thing. Okay, go on.
Okay, that's a good point. I'll look it up. There's this book by Batten, and I forget the other person's name. It's called Linear Spaces, and actually it starts like this. So, all right. So today we're going to do lattices, completely different from what we've been doing so far. And it's just really amazing that Matroids has all these different perspectives. And the material today, I don't think is very difficult, but I'm not a lattice expert, so I just hope I don't make any mistakes here. All right. I'm going to start with a partially ordered set for the students in the audience. A partially ordered set or also called poset, is a set P together with a relation, and you can call your relation whatever you want in here for partially ordered set. It's like a stylized less than for because less than is like the less than or equal to is the original partial order that satisfy 3 properties. X is less than or equal to X, that's reflexive, right? If X is less than Y and Y is less than X, then X is equal to Y. So instead of equivalence relation would be symmetric, right? And this one is anti-symmetric. And 3, if X is less than Y and Y is less than Z, then X is less than Z, and that's transitive. So we're starting from scratch, literally, as in the partially ordered sets, okay? So example 1, natural numbers with less than or equal to, that's a great partial order, right? It's what's called a total order because you can line them all up. But what about this one? The power set of S with inclusion, subset relation. And let's suppose we just have 1, 2, 3, right? So, and then we can draw this great Hasse diagram, right? And that's 1. How is it pronounced? I think it's Hasse. 1, 2, 1, 3, 2, 3. And of course, everything else. And you can see from that example up there, that's a geometric lattice. That's where we're headed. The set of flats of a matroid are a geometric lattice, form a geometric lattice. So there we have, the simple example of partial order. And let's do a couple more just to make sure. The set of divisors of n with, well, the division relation. So for example, if you're doing D24, right? Well, we have 1, then 3, 2, right? 6, 4, 12, 8, and 24. Right? And if you have the 30 divisors of 30, you get a shape that's very similar to example 2, 6, 10, 15, and 30. And 2 cosets, P1 and P2, are isomorphic if there is a bijection. It's the one that you would sort of expect, from P1 to P2, such that x is less than y if and only if f of x is less than f of y. And in our example, D30 is isomorphic to the example 2 over there, right? And you can see that in the Hasse diagram. So that's partially ordered sets for you. And now let's do least upper bound and greatest lower bound, also called join and meet. Is this clear? It's just a very different from what we've been doing earlier, like graphs and stuff. And feel free to stop me anytime if I need to go slower or anything, all right? Less than or equal to looks like alpha. So be a poset, and AB is in 2 elements in the poset. The least upper bound, also called the join of A and B, denoted like this, A or B, is defined as A is less than A or B, B is less than A or B, and A is less than C, and B is less than C, implies A or B is less than C, right? So you have 1, 2, fairly obvious, and 3 over here. Similarly, the greatest lower bound called the meet also of A and B, written like this, A and B, is defined as A and B is less than or equal to A and B is less than or equal to B. We call that the relation, the partial order relation, less than or equal to. I use it interchangeably. It's neither, it's not less than or equal to, it's whatever the relation is. C is less than A and C is less than B implies C is less than A and B. Excuse me. And you have AB, so that would be a join, and this would be a meet. And a lattice, all right? So this now the next definition is that of a lattice. A lattice, let's call it L, is a poset such that for every pair of elements A, B in L, right? A or B and A and B exist. So actually our examples here, I think, are lattices. And if you want to see a partially ordered set that is not a lattice, just sort of take out one of these entries, right? So you take out something there and you'll get something that's not a lattice. So the example that we're interested in is the flats of a matroid M, defined as earlier, with containment, that's a subset relation, is a lattice. So, and we'll call this lattice LM, right? So why? I mean, it should satisfy, it should have, every pair of elements should have a join and a meet. And then if you look at the flat axioms, right, where were they? The flat axioms were here, right? So I think flat axiom number 2 tells us that if F1, F2 is a flat, then the intersection is also a flat. Rebecca, yes.
Do we need to have uniqueness for the lattice? That the join and meet need to be unique, or do they just need to exist?
Oh, that's a good question. I know. I
think I've usually seen the definition with uniqueness, but it might not change anything either way.
I think they have to be unique, at least certainly all the examples. And I was, in this, that's a good point. So definitely something that I need to look into. So I'll just.
Oh, Sandra, I think that if you were to have two different meets, say, your definition of meet would mean that they need to each be less than each other.
And then by isometric, they'll be equal to.
Yeah.
Right?
Yeah, I think that tracks.
Yeah. Thank you so much, Mike. Thank you so much. Yeah. Yes. And also in this discussion, we're just going to do simple lattice, simple matroids. That means no parallel edges and no loops. Because, you know, loop would be in every flat, and we just like not talk about it. So why? Well, let F and G be a pair of flats. Then F or G is the closure of F union G, right? And that's a flat. And F and G is F intersection G, and that's by flat axiom 2 is a flat. All right, okay. So now we're going to talk about a graded lattice, which I'm going to put down the details, but the idea is right here. You have these levels, right? It's graded is a word to express that there are these levels. All right, graded lattice. So let P be a poset and A, B, and P. We say A covers B if A is less than B, right? And there is no element in between. A lattice is graded if there exists a height function h from two natural numbers, such, I suppose, union 0, because the first one is 0, such that the least element has height 0. And if y covers x, then h of y is equal to h of x plus 1. Okay? So we're going to show that our example of interest, LM, is graded. And the height function is the rank function. So I should mention that I did, 3 of the simplest examples of partially ordered sets and lattices, and then went straight to matroids. There's this vast literature on on lattices. For example, the faces of a polytope form a lattice called the face lattice. And there's all sorts of other examples that are sort of deeper than the ones that I gave. So LM is graded and the height function is the rank function. So reason, then the rank of phi is 0, right? So the lowest level. And keep that example in mind, the big one that we had earlier with all this one. This one is a good one to keep in mind. It's just like 2 layers, but just if it was 4-dimensional, there'll be 3 layers and so on. Okay, just imagine n-dimensional and there'll be n-1 layers there. Okay, and then 2, suppose G covers F and let X be in G minus F, right? What are we aiming for? We want to end up with rank of G is equal to rank of F plus 1. All right, that's where we're headed. So F is a subset of F union X is a subset of G, okay, right? And then closure of F is contained in closure F union X. It's contained in closure of G, right? Agreed? Because that is one of our closure properties. If A is contained in B, then closure of A is contained in closure of B. Now, closure of F is just F, right? So F is contained in closure of F union X, and then closure of G is, I guess I should say F and G are flats here. Sets, and closure of G is just G. So we have rank of G is equal to rank of the Mr. Line, since G covers F, closure of F union X is also G, right? That's my hypothesis. Since G covers F, closure of F union X is equal to G. And is that the reason? No, I don't know if that's the reason. I think it's because you have X in G minus F, right? I think that's the reason. Closure of F union X will be G. Yeah, so I don't think this is the reason. Almost done. So what do we have? So rank of G, rank of G is rank of the closure of F union X. That's rank of F union X. And F union X is rank of F plus 1. Right, so rank of G is the rank of the closure of F union X. Right, and that's rank of F union X, which is rank of F plus 1. All right, so that follows from those flat and closure axioms. And that property that I mentioned after that. You have a flat, then rank of F union X is rank of F plus 1. Okay. Should we move on? So let's talk about semi-modular lattices, a finite lattice. I suppose all our lattices are finite. Didn't mention it before. L is semi-modular if it is graded and for every pair of elements AB in L, the height function satisfies the semi-modular property. See, usually when you have a set, right, size of A union B is equal to size of A plus size of B minus size of A intersection B, right? And semi-modular is just less than or equal to. Okay. So why is a favorite example semi-modular? Because the height function, which is the rank function, satisfies this. In fact, that's the rank axioms. The rank function has to satisfy this. That's what makes it semi-modular. And actually, I'm hoping that when we go through this, the reason for some of those axioms becomes clearer. As in, why did we have the rank function semi-modular? Well, lines up over here. A finite semi-modular lattice is atomic if every element is a join of elements of rank 1. And intuitively, right? Intuitively, that's just like obvious intuitively, but you have an explanation to go through, right? All our flats are basically unions of 1, 2, 3, 4, 5, 6. And that's what makes it atomic. And our example LM is atomic. And what's our reason? Besides intuitive reason. So let F be a flat, right? Then for every F in F, closure, that's little f over there, every element F in capital F, the closure of F is contained in F. So we can write F as the union of all its elements, which is the union of all the closures. And that's contained in F, because every closure is contained in F, right? So equality holds throughout. So F is the union of the closure of all its elements, right? Essentially, this side is obvious. We did the other side to show equality. Couple more lines here. So closure of F, which is F is a flat, is equal to the closure of all the unions of the, is the closure of the union of the closure. Right, little tongue twisting there. And that is F. So we have F is equal to this. And this is just the join of rank 1 flats. Yeah, so I mean, that's the basic idea, the intuitive idea that F is, suppose F is F1 to Fk, right? Each of these are the rank 1 elements, right? The ones at the bottom. And you can write that as this. Yeah, so L of M is atomic, right? Almost done, right? Any questions? A lot of little details and application of the axioms. So a finite semi-modular atomic lattice just the name given to it is called a geometric lattice. And that's a great name because, you know, this is what matroids are. They're combinatorial geometry. So calling this a geometric lattice is just really a great name there. And Birkhoff did this, I think, just like a year or 1 year after Whitney's paper came out. Yeah, so we did one direction, right? So a lattice, so this would be theorem 17. A lattice is geometric if and only if it is the lattice of flats of a matrix. And this differs a little bit from the graphic perspective on matroids, as we called it, and, you know, coordinatizing matroids and getting the over finite fields and getting that big class of what we call representable matroids. This is slightly different in the sense that a geometric lattice is a matroid. It's not like a subclass of matroids. It actually is a matroid. So proof, which direction is done? This one, this direction. Given that L M is the lattice of flats of a matroid M, right? To show L of M is geometric. Right? That would be all the arguments above, right? This is the one that showed it's atomic. Then we had the rank function became the height function, and this reason here. And then the other direction, in keeping with what we've done, if every other direction, that is like too much work and it's in the book. I'll just set it up. Given L is a geometric lattice, right? We want to show that L is the lattice of flats of a matroid. Right? So essentially, you define a rank function, and then that becomes that rank function will satisfy the rank axioms, and that's what makes it a matroid. So let E be the set of atoms. Okay. And define the rank function we define this way. Rank from should be n union 0, right? I always forget the 0. And rank of E1 to EK, right? Some subset of E, almost there, at least almost at our stopping point. That's equal to rank of E1 or E2 or EK. And this R will satisfies the rank axioms. So in all the previous sections too, we just did one direction and left the other direction to be looked at in the book. But if you took a look at the notes, I actually scanned the appropriate paragraphs in the book and insert it. Like I'll do that here too. I'll scan the appropriate paragraphs and insert it here. So the notes that are posted are a little bit more complete and actually also neater than these notes. Okay. So this is a lot of work. And then there's another theorem that needs a little bit of work too. So let M be a simple matroid, and that's sort of the assumption that we made in all our examples. Then L of M uniquely determines M. All right. So in the last 15 minutes, I wanted to do a slightly different approach to lattices that I found in another book that I thought was really interesting, and it ties into Kira Darisheva's anti-matroids. And actually, I don't know if she's here. I'm hoping she gives an anti-matroid talk, teaching talk like this. So because it has a bit of a learning curve, and it's just really just the opposite of matroids. But how is it the opposite? That would be really good to know. Okay, so this is from somewhere else, right? So we can think of a lattice. So this is the way this book introduced lattice. Let's just call it a node. We can think of a lattice. So lattice again, but slightly different approach, as having two operations the meet and the join, such that, and the definition given was, now I'm just going to write those properties of meet and join that we had earlier, right? So they were spelled out here for meet and join. Yeah, see those things? I'm just going to write that down. So think of it as having two operations. X is less than X or Y, and Y is less than X or Y. And if X is less than Z and Y is less than Z, then the join is less than Z. And two, just a minute. Then yeah, and X. So this is X is X and Y is less than X, and X and Y is less than Y. And if Z is less than X and Z is less than Y, then Z is less than X and Y. All right, just think of the lattice like that. Now these two operations are commutative and associative. That can be checked. Are commutative and associative. And then we'll define isomorphism, right? How did we define it earlier? We just said if, where is isomorphism? Yeah, there's a bijection, right? We defined earlier two partially ordered sets P1 and P2 isomorphic if there's a bijection from one to the other such that X is less than Y if and only if F of X is less than F of Y, right? So we'll define isomorphism. And this is the same, it's not a different definition, it's just kind of a different way of thinking about it. If there exists a bijection phi from L1 to L2 such that phi of X or Y is equal to phi of X or phi of Y, and phi X and Y is equal to phi of X and phi of Y. So from this approach, we didn't have a definition of distributive lattices earlier. Now we do. A lattice L is distributive if for every X, Y, Z in L, X and Y or Y and Z or Z and X, right? So you got all of them there, is equal to X or Y and Y or Z and Z or X. And the reason I wanted this definition of distributive is because antimatroids are a special kind of distributive lattices, right? And L is, in this approach, L is modular if for every X, Y in L, Z is less than X, implies X and Y or Z is equal to X and just like associative property. Okay. And it's semi-modular. I should check that, make sure that's written correctly. And it's semi-modular, which, what did we have semi-modular as earlier? Yeah, semi-modular, if it's got that, if it's graded, that it's got that rank function that has those, it was called heights. For matroids, it's rank levels, right? So that's semi-modular. And in this approach, L is semi-modular if for every X, Y in L, X and Y covers implies X or Y covers, sorry, sounding a little tongue twisting here, X and Y. And basically you have modular flats, distributive lattices are inside, not everything, there's not, no great containment relations between all of these things, but distributive lattices are a subset of modular flats, and semi-modular is outside that, that's matroids, and anti-matroids are some kind of distributive lattice. And then you have these beautiful propositions that they have the same flavor as graph theory, actually, but just take a look at it. So L is distributive if and only if L has no sublattice, and I should probably define a sublattice, isomorphic to these two lattices. This is let's just draw the Hasse diagram of them. This is called D5, and I think this is not a cycle. This is a Hasse diagram of a lattice. This is P5 or something. No, yeah, you're right. This needs that. So you don't have these two structures. So what's a sublattice? This is big picture, okay? This is just sort of the kind of results that you have in lattice theory that I don't think have been used in Matroid theory as yet. It's a little avenue of work over there. So L dash is a sublattice of L under what conditions? For every x, y in L dash. I don't know if it needs a definition. It's just like a substructure of the Hasse diagram. X or y and x and y are in L dash. That's essentially what it's saying. It's just a sublattice, like grab the joins and the meets, all right? For every pair of elements in the sublattice, the joins and the meets should be in the sublattice. And we have, another one like that, L is modular if and only if L has no sublattice isomorphic to this one. This is a Hasse diagram. And my question is, I wonder if there's something geometric. So this is my question for anyone who knows. So I wonder if geometric lattices also has some kind of structure like this. Like it's almost like, looks like an excluded minor result, right? Except it's not graphs, it's lattices. Then the quick thing about chains. By the way, if you want to keep an anti-chain in mind, think of just the lattice of natural numbers, right? And think of the primes, right? No one prime will be less than or not. I guess I said that wrong. This one, the divisors, not natural numbers. We want this one. Think of this one here. Here we go. All right. In this lattice, the set of primes, no one prime will be a divisor of the other. And as Euclid proved, there are infinite number of primes. So that's what an infinite anti-chain is. And what's really amazing, the graph minors theorem, is that the set of graphs with the minor relation doesn't have that. There are no infinite anti-chains in graphs with the minor relation. Just think about that. It's set of graphs has less structure than the natural numbers. I mean, that's not what I meant, but it has more structure than the natural numbers in the sense that no infinite anti-chains. Okay. A set of elements x naught less than or equal to x1 less than or equal to xk is called a chain. from x naught to xk of length k. All right, just one less than or equal to the other in the partial order. The length of the chain is k. And a chain is maximal if xi covers xi minus 1. Our definition of covers was earlier. The height of x is the least upper bound of chains 0 less than x1 k equals x. So partial orders here. And if all maximal chains have the same length, then P satisfies what's called the Jordan-Dedekind condition. So think of chains intuitively. You have chain, you can go this way, you can go that way in the lattice, and there's a top that you can't go any further, maximal chain. So last proposition of the day, L is semi-modular, right? This is the subclass where you have matroids, if and only if L satisfies the Jordan-Dedekind chain condition, and its height function H semi-modular, right? That part is the same. There we go. So, right, what did we decide earlier? That a finite semi-modular atomic lattice, atomic is not a big condition there, you just have to have those base elements, is a geometric lattice, and you almost have this characterization. Doesn't say anything about being atomic here, but throw in atomic and you'll have matrices. Very, very different appearance of matrices. And this is a good place to stop. I'll stop the recording and take questions, just in case I can't answer any of them.